Hello friends, welcome to Active Event Academy. In the last lecture, we have completed the discussion on the strings in 2 dimension. Also, we have seen important results on the strings in 2 dimension. Okay, so in this particular lecture, we will start solving the problems on the strings in 2 dimension. So let us revise those important results. So what we have seen in the previous lecture is that the important results are, so we have the intrinsic equation of common catenary. The intrinsic equation of common catenary is S is equal to C tan psi. Okay, and we have the Cartesian equation as Cartesian equation of common catenary. The Cartesian equation of common catenary is so we have y is equal to c cos hyperbolic h x upon c, and the parametric equation as parametric equation of common catenary. Parametric equation of common catenary is x is equal to c log sec psi plus tan psi, and we have y is equal to c sec psi where psi is parameter. Okay, and other relations are, so we have the tension at the bottommost point is weight of c length of the string, that is w into w is the weight per unit length, and length of the string is small c, so T naught is equal to WC. Also we have seen the tension is proportional to the ordinate. Okay, y is the distance of the point from the axis of x, that is directrix. So T is proportional to y. This means T is equal to small w into y. Okay, weight per unit length into ordinate. This is tension is equal to Wy. Okay, and tension at bottommost point is T naught is equal to Wc. Okay, also we have seen S is equal to C sine hyperbolic x upon c. Okay, and using this particular expression and this particular expression, we have y square is equal to c square plus s square. Okay, so this all we have revised in the previous set of lectures. So this particular expression is important, this is important, this is also important, and these two expressions are important. Okay, now let us start solving the problems. Okay, so what is given in question number 1? If the normal at any point P of a catenary meets the directrix at Q, show that PQ is equal to rho. So let us solve this. So we have the catenary like this. This is the catenary, and this is the point where it is tied. Okay, so let us take this as, this is the horizontal line, this is point B, this is point C, and this is the bottommost point. Let us take this as A, and this is the axis of x, that is directrix. Okay, and this is the axis of the catenary, that is axis of y. Okay, this is point, let us take this as point A. Okay, so what is given in the question? Normal at any point P. Let us take this point as P. Normal at any point P of a catenary meets the directrix at Q. So this is directrix. Normal at any point P meets the directrix as Q, and we have to show that PQ is equal to rho. This we have to show. Okay, now let us draw the tangent at point P. Okay, this is the tangent at point P, and let us take this tangent makes an angle of psi with the horizontal. Okay, and let us take the coordinate of this point P as x comma y. Okay, so this is the axis of x. Okay, so this distance will be y. Let us take this point as t, this point as PM. Okay, so we have to show that this particular distance, that is PQ, is equal to rho, that is radius of curvature. So this angle is psi. This angle is also psi, and this is 90 minus psi. Okay. Now let us take this particular triangle. So in triangle PMQ, in triangle P1Q, sine of 90 minus psi, sine of 90 minus this particular angle is equal to, this is PM upon PQ, PM upon PQ, height upon hypotenuse, PM upon PQ. PM is Y and PQ, let us take this as PQ. Okay, so this is cos of psi. Cos of psi is equal to Y upon PQ. So PQ is equal to Y upon cos psi. Cos psi. So this is Y sec psi. Okay, so this is PQ is equal to Y times of sec psi. Okay, and we know that Y is equal to C sec psi. This we have already discussed. Okay, so this is the parametric equation. This we have discussed in parametric equation of common catenary. Common catenary where psi is parameter. That is, the parametric equations are x is equal to c log sec psi plus tan psi, and second equation is y is equal to c sec psi. So these are the parametric equations. So let us place y is equal to c sec psi. So PQ is equal to c sec psi into sec psi. So PQ is equal to c sec square psi. Okay, PQ is equal to c sec square psi, and we have the radius of curvature as ds upon d psi, and the value of s is c tan psi. So rho is equal to d upon d psi of c tan psi. This is equal to c times of sec square psi. So the value of rho is c sec square psi. This means c sec square is equal to rho. Okay, so let us take this as equation 1 and this as equation 2. So from equation 1 and 2 we have PQ is equal to rho. Okay, so now let us discuss question number 2. So what is given in question number 2? If T is the tension at any point P of a catenary and T naught be the tension at the lowest point A, prove that T square minus T naught square is equal to capital W square, W being the weight of a arc AP of a catenary. Okay, so let us discuss this. So we have a catenary like this. Let us draw the catenary. This is our catenary. Okay, and this is the point where it is hanged. This is point B, this is point C, and this is lowest point A. Okay. This is the axis of y. Okay, so we have the T be the tension at any point P. Let us take this as point P. So T be the tension at any point P, and T naught is the tension at lowest point. W being the weight of arc AP of a catenary. So this is our point P. Let us take the arc length as S. Okay, and weight per unit length is small w. So weight of string of arc length S. Okay, so this is the S is the arc length, that is arc length of this is S is the arc length AP. Okay, so AP arc length AP is equal to S. Okay, the weight of a string of arc length S, that is this is equal to capital W. This is W being the weight of arc AP of a catenary. So this we have taken as a small s. Capital W is equal to small w into S. Okay, so small w is weight per unit length. Okay, this is capital W. Okay, so let us resolve this. So this is the T at point P. We have the tension as T. So this will make an angle of psi with the horizontal. obviously. So the horizontal component is t cos psi and vertical component is t sin psi. So the horizontal component t cos psi is equal to t naught, and the vertical component will be equal to weight of this string. This will act at this particular point at the center of gravity. So this is equal to a small w into s, weight of s length of the string, and this is equal to capital W as given in the question. So capital W is equal to small w into s, and this is equal to t sin psi. Okay, and we have the value of t naught as t naught is equal to, this is the horizontal component, so this is t cos psi. Okay, so let us square and add this. This is equation 1, this is equation 2. So squaring and adding. This is capital W square plus t naught square. This is equal to t sin square psi plus t square cos square psi. Okay, so W square plus t naught square is equal to t square. So we have to prove that t square minus t naught square is equal to capital W square. Okay, so now let us discuss question number 3. To prove that in a uniform inextensible chain hangs freely under the gravity, the difference of tensions at points varies as the difference of their heights from the axis of x. So let us draw a common catenary. This is a common catenary. Okay, so these are the 2 points where it is hanged. Let us take this as B and this as C. And this is axis of x and axis of y. So this is axis of x, that is directrix, and this is axis of y. This is the axis of the catenary. Okay, so this is x axis, this is y axis. Okay, difference of the tension at 2 points. So let us take 2 points. Let us take these 2 points. Okay, so let us take the tension at this particular point as T1, this as T2. Okay, now let us take, take this as T2. T2, this is T1. Okay, and let us take the coordinate of this point. So this is point P, this is point Q. The coordinate of this point is x1 y1 and this is x2 y2. Okay, so we have studied in the relations under the common catenary is the tension at any point P is proportional to the ordinate distance of this point, that is distance of this point from the axis of x. Okay, so distance of this point P from the axis of x is y1, distance of this point from the axis of y is y2. Okay, so the T1 is proportional to y1 and T2 is proportional to y2, and the relation between tension and the ordinate is tension is equal to weight per unit length into y. Okay, so let us consider the weight per unit length as small w. Okay, so we have T1 is equal to small w into y1 and T2 is equal to small w into y2. So T2 minus T1 is equal to w times of y2 minus y1. So T2 minus T1 is proportional to y2 minus y1. Okay, so what is given in the question? Prove that if a uniform inextensible chain hangs freely under the gravity, the difference of the tensions at 2 points varies as the difference of their heights from axis of x. Okay, so these are the heights from the axis of x. So difference of tensions at 2 points varies as difference of heights, difference of their heights from axis of x. Okay, so now let us discuss question number 4. Show that for a common catenary x is equal to c log y plus s upon c. Let us discuss this. Okay, so for this question number 4, okay, what we have to show? To show x is equal to c log y plus s upon c. Okay, so we have the intrinsic equation. So we have the intrinsic equation of common catenary as S is equal to C tan psi, and parametric equation as x is equal to C log sec psi plus tan psi, and y is equal to C times of C sec psi. Okay, let us use these equations, these three equations. So this is equation 1, this is equation 2, this is equation 3. So from equation 1 we have tan psi is equal to S upon C, and from equation 3 we have sec psi is equal to y upon C. So let us place this value in equation 2. So we have x is equal to C log, value of sec psi is y upon C, this is y upon C, plus tan psi is S upon C. So x is equal to C log y plus S upon C. Okay, so this is the value of this we have to, so x is equal to C log y plus S upon C. Okay, so we have discussed up to question number 4, so we will discuss further questions in next particular lecture. Thank you.